Okay, everybody, good afternoon to you. So I just want to let you guys know that if we take a look, I have a course. You guys know I graded your test 3. It is in Canvas. I do have test solutions as well. You guys can take a look at them, see where you went right, where you went wrong on the test solutions. They're there online. Also to remark, you're not statistics, which is fine. You are calculus. But to remark to you guys, come Monday, we have test number 4 here. Okay, so we're in the last few weeks. Oh, that's kind of not right. We got to update your schedule. No, 262. Somehow it's not going to 262. There we go. So to look at your schedule, the last few weeks, ladies and gentlemen, we're going to have our test on Monday, May 22nd, test 4. So I just kind of want to remind you guys, and then the following week, you're going to have your final exam. So, anyway, so that's what's happening. And just want to let people know as a reminder, because sometimes people are asleep and they're not even awake yet. And sometimes they wake up at the end of the semester and they go, okay, what's going on? And so we're just kind of talking a little bit about what's going on now. Today, we're still working with series today. And like I said, we're now working on various tests for series. Like we had the integral test last time. This is really today the limit comparison test. But it's first based on what we call the comparison test. Now, I don't really spend much time at all on the comparison test. It could be a very difficult test to apply. And again, there's always very specially chosen questions for comparison. And it's based on a very simple premise here, the comparison test. But what we do is we look at the comparison test and then we develop what's called the limit comparison test. And that's really what we want to look at, is the limit comparison versus comparison. But here's what we really want to start with. We're going to assume we have two series, okay, because we're going to now compare two series. And we say, assume we have series, these are two series, with what we say positive terms. Okay, this is a vital component. So we're going to have two series with positive terms. Now, what that means is to say that they both have positive terms is that both, here's what that means. An is greater than 0 for all n, and Bn is greater than 0 for all n. So that's what the assumption is. They just have all positive terms, meaning they're greater than 0 for every term. So that's what we're assuming. Okay, now this is kind of a logical statement here to let you guys know. Number one, we're going to let an be less than or equal to bn for all n, okay? So the terms of my series here for an are really smaller than the terms for bn for every n. Okay? So we're going to let that happen where what we're really saying is that all the terms, when we add every term, we get the sum of an is less than or equal to the sum of bn. Okay, so let me go back and show you guys what we're really saying here. Okay, so we take one sum, we have another sum. What I like to say here, we have the smaller series. And here we have what's called the larger series. Okay, so this is true. You know, if we let AN be smaller than BN for all n, then really what happens is you got a smaller series and a larger series. Okay. So here's our first criteria. So what we say is this: if the larger series converges, I'll write that down that way. If the larger series converges, okay, then what does that force the smaller series to do? So this is, again, this is your assumption. The bigger series is finite. That sum is less than infinity. It's a finite sum, if I can draw an ellipse there. Then what does that mean about the smaller series? And you can guarantee then that the smaller series is forced to also be what? Convergent. Is that true? Okay, because you have the larger series being a finite value, then what this really means, it forces the smaller series to be finite. That's what we're looking for. Just by comparison. Yeah. No, they're not the same function. They're different series. So you have two series here. So this is comparison. You have what we say two series now. This is why you're comparing. This is your AN is your first series, and BN there. Some AN is the first series, some BN is the second series. And in some ways, we can write it this way. I don't think your book writes it this way. That's the first fact. And I'm going to write it a little differently than the book, but it's really equivalent. Okay, so the larger series converges implies that the smaller series converges. Okay, now, second thing that we know is this. If the smaller series AN diverges, again, this is a smaller series now. So if the smaller series is too big, because remember, we're comparing series there. This is a comparison. So now the smaller series is too big. It goes to infinity. Then what that's going to force happening is that the bigger series is also too big. It's divergent. Okay? So smaller series diverges implies that the larger series diverges. This is the second most important fact. Okay, so this is what we say by comparison. Generally speaking, that's very hard to show, generally speaking. Very difficult to show. Okay, now all the terms are positive. and you got a smaller series and a larger series. Okay, if the larger series is finite, the smaller series is finite. If the smaller series is infinite, the larger series is infinite. Okay, and now you say, okay, that's very difficult, and the book has some examples. But what we're really going to study is what's called the limit comparison test. This is the essence of what we're doing, limit comparison. And it's the same situation that we're going to say. We're going to have two series. We're going to say let these series, AN and BN, be two series. Okay, they're two different series. With positive terms. Okay, so they have to have positive terms. Here's my first series. Here's my second series. The terms are all what? Positive. So that's the assumption. Okay, so they're going to have all positive terms. I'm going to move it all down here. Okay, so that's setting the table. Now, if the limit here of the ratio of the terms A and Bn, if that limit equals C, now you say, what do you mean, what is C? Has to be finite, so I'm going to say this. C is finite and positive. So that's all we're looking for, a finite positive number. If you have that, then this is what we can say. Okay, we can say either both series converge or both diverge. So this is really a very powerful fact. And I'll show you guys how to use the limit comparison test. But this is actually what we're going to do. We're going to use the limit comparison test. This is a test for either convergence or divergence. But it really is based on this criteria right here. Right? You need the limit to be finite and positive. If you have that, then you have the conclusion. Okay? But I'm going to give you guys the proof here. So let's prove this to you guys because that's important too. Here's a proof of this. Okay, we're going to consider two numbers that are both positive, such that little m is less than c, which is less than big M. Okay. So remember what you have here with the assumption. This is my assumption that the limit of this ratio equals C. Okay, because we're assuming that. So I want you guys to always know that that is your assumption. That the limit as n goes to infinity of that ratio AN over Bn is C, where C is finite and positive. So all we're going to say is assume that, you know, AN over Bn, right, this is close to C. For some value, you know, n bigger than that natural number. In other words, what we're saying is little m is less than that AN Bn value, which is less than that Bm value, that big M. Okay, so then now just multiplying bn to both sides, we get m less than, well, multiply bn to both sides here. This is the denominator. Remember, bn's positive. So we get m bn is less than an, which is m bn, again, at some point for n. So this is really the bottom line criteria here that we care about. Okay, so we get all of this just by assuming the limit is finite and positive right there. This is your assumption to the proof. Okay. So then you say, well, how can I conclude that both converge or both diverge? Well, here, let's notice this. If the series Bn is divergent, okay, then what we know is M sum Bn is also divergent. In other words, the series An, which is bigger, diverges as well. So I say this is diverges by the comparison test. So this is what they're saying. If this series diverges, then this series diverges. They both diverge. Because of this relationship you guys see up here. And then you can say also, similarly, if the series An converges, the larger series, then we know M sum Bn is also finite, the smaller series, i.e. sum Bn is finite. So now they're saying if An is finite, then so is Bn. And it's all based on what you see in here. Now, this is why they have that conclusion. And this is why they call it the limit comparison test. So this is what we want, really. Okay? This is what we're going to end up using. And because all the terms are positive, you have these nice relationships that they outlined here. And this is really the proof of what you're trying to do. So they always start off with this very simple example here. And in the examples in your book, you have this particular series here. Okay? This is the book's example. Now, here's what's going to happen, ladies and gentlemen. Here's how to use this particular comparison test, okay? That's your series An. What you need is another series Bn to compare it to. Okay, so you need two series. It's a comparison test. But then you might say to me, how do we compare it to this particular series right here, right? In theory, you can compare it to any series of positive terms, in theory, because there's no criteria here. All the criteria is you need two series with positive terms. Okay? And you're going to look at this particular limit and see if it's finite. If it's finite and positive, then you know you can use the limit comparison test. But the question's going to always be, what can we use for this series? Okay? What can you use? Has to be a series of positive terms. Now, here's what I'm going to say to you guys, what you guys want to do. What I do here, or what the book does, what people do, how you actually use this. You see this particular series? I'm going to use a series that looks very similar to this series. You go, how do we use a series that's similar to this? Well, can I tell you guys something? You see where the constants are? There's a constant here, -1, right in here. Is that true? See that -1? So what you can do to get the BN series, very often we say this particular series behaves like this series. If I remove the constant, did you guys see what I just did? I removed that -1 for the denominator. And all I'm saying is that particular series, AN, behaves like this series here. Okay? This, ladies and gentlemen, is the BN, some BN. This is my BN term, right in here. Okay, you guys okay with that? Just remove that constant, and they're very similar series. So now, if you say, what do I do? Now look at the limit of the AN term over BN. Okay? Well, that's going to be the limit now, since AN is 1 over 2n minus 1, and BN is 1 over 2n. We're going to have to do some algebra right in here, ladies and gentlemen. Okay? I use gray. So you say, what is this algebra going to be? One over 2n minus 1 divided by 1 over 2n. One over 2n minus 1 times 2n right in here. That's 2n over 2n minus 1. Okay, we need to find what this limit is. Now, you might say, I don't know what that limit's going to be. Well, let's do a little bit of Calculus 1-ish. This is kind of Calculus 1-ish. You didn't see this exactly in Calculus 1. You've seen something very similar in Calculus 1, right? Limits at infinity. Here's what I'm saying. I'm going to look at the denominator, and I'm going to divide every term by that 2n, right? Because we did something like that in what? In Calculus 1, although it was like, you know, x to the second power, right? The variable to the largest power. So it's a similar approach to that course. Now you say, what does that mean? I get 1 over 2 to the n power now. Do you guys see what that just did? And so now, by properties of limits, where does this limit go to? Where does this converge to? Do you guys know what happens? Does it 1 over 2n, where does that go as n gets big? Doesn't that go to 0? So then this limit is really going to be 1 over 1 minus 0, or really just the number 1 over 1, which is 1. What do you guys know about the number 1 here? Isn't that positive and finite? So I put that greater than 0. So what I'm showing you guys is this, that the ratio, the limit of the ratio of AN over BN is positive and finite, okay? So what this means is both series converge or diverge. Now, this is your conclusion. Both what? series converge. Why do I know both series converge? What do you know about this series? This series what? Converges. So this is why we can say both series converge. Because I know that this series converges. How do we know that this converges? This is a what? Isn't this a geometric series? Where r equals 1/2? That's a geometric series. R is 1/2. So what that means, ladies and gentlemen, is at the end of the day, here's your conclusion. Since you know that this series converges, the series that you compared it to converges, we say by the what? By the limit comparison test. So you got convergence by the limit comparison test. And there it is, ladies and gentlemen. This is what we're starting to do. We're going to use what's called the limit comparison test. It's a pretty big deal. Okay, and we're just comparing it to a series we know that either converges or diverges. That's the idea. You're going to compare it to something you already know. For example, n cubed over n to the 4th minus 1. Okay? We're going to compare it to something that we know either converges or diverges here. So that's the series AN. Behaves like n cubed over n to the 4th. Why do I want to say that? Behaves like this. What do you do, ladies and gentlemen? You just get rid of these what? That constant. All right, you guys see what I'm saying? Get rid of the constant. Now, if I get rid of the constant, that means I really have the series from 2 to infinity, 1 over n. This here is the Bn. So if I want to use the limit comparison test, that's what I'm doing. I need to look at the limit of AN over BN. I need to find that if that ratio there is finite and positive, I can say something by the limit comparison test. Okay, so at this point here, we're going to use that complex fractions here. So now, what is this limit going to be? Do you guys know what this limit is? Yeah, that's also 1. You say, how do I know? Calculus 1. You put n to the 4th power. Sorry about that, my chicken scratch. 1 over 1 minus 1 over n to the 4th now, right? And that limit is 1. You say, what's so nice about this? Well, finite and positive. This is what you're looking for. So you say, well, what's my conclusion here? We'll go back. What do you guys know about this series? That is the divergent what? Harmonic series. We've seen that already by the integral test. This diverges. So then what does that mean about this series? This series also diverges. Okay? But what you want to say is something like this. You want to say this. Diverges by, I abbreviate this, limit comparison test. Okay, compare that to something like this. This is n minus 1 over n squared square root of n. Okay? This is the an. Okay? Now, that series behaves like, you say, what do I do with that series? What do you guys think you do? You get rid of this what? Get rid of the constants. So you got n over n squared square root of n. Do a little bit of algebra here, ladies and gentlemen. Isn't that going to be 1 over n square root of n 1 over n to the what? 3/2. Okay, that's going to be the Bn now. So as you do your limit, n goes to infinity of the ratio an over bn, that's your limit of n minus 1 n squared 1 over n to the 3/2. Okay, you guys have that here? So what happens here with our limit? You got n over 1 times n to the 3/2, and then this is n to the 5/2, I think. Is that true? So this is going to be n minus 1 over what? N. Is that right? I think so. And what does this limit become? 1 minus 1 over n. And that limit is 1. And again, that's positive and finite. Okay, you're using the limit comparison test. Positive and finite. So, what does that mean about the series? Do you guys know anything about this series, by the way? What is this series? This is called a what? Convergent p-series. So that's a convergent p-series. What does that mean? That this series also what? Converges. So this converges by the limit comparison test. What do you guys think? Easy peasy? limit comparison test. I want to move this down. Okay. So we're going to take a look at this series. This is my AN. And then we say this series behaves like what happens when you remove your constant in the denominator. Right? This is what I just said here, right? We're going to remove that -1 here. You're going to remove this particular constant, and then so the AN series behaves like this one. So you might say, well, what am I looking at? Do you guys know what this is? This is really a divergent geometric series. Is that true? So I want you guys to note something here. This is that divergent geometric series. Because R is actually 6/5. I just want you guys to know. So really, the limit comparison test says I have to look at the limit of the ratio AN to BN, which is going to be the limit now of what? 6 to the n, 5 to the n minus 1 over 6 to the n over 5 to the n. Limit. 6 to the n okay. And then you could cancel this, and you say this is the limit now. 5 to the n over 5 to the n minus 1. Is that true? All right, we got cancellation for that 6 to the n. So what do you think is going to happen with this? Okay, again, just like you can look at this as a calculus 1 kind of question. You divide every term with that 5 to the n, 5 to the n, 5 to the n, and then you get this what? Limit, n goes to infinity, 1 over 1 minus 1 over 5 to the n, and then that limit is 1 again, which is finite and positive. All right, so since that limit is 1, which is finite and positive, and we know this particular series is a divergent geometric series right here, that means this series also diverges by what we say the limit comparison test. So here's an example of the limit comparison test. It diverges as well. Okay, now they give me 2k minus 1. Here, how about this one here? 2k minus 1 times k squared minus 1 over k plus 1 plus k squared plus 4 squared here. Let me double check. Let me see. Yeah, sorry. No, that's okay. I think I have a typo on this one here. Have a typo. Don't worry about that one. We're going to say this. We got the square root of n over n minus 1. I didn't find that one. All right. There's your an. This series behaves like, what does this behave like? If I get rid of this constant, what do you guys have? Isn't that square root of n over n? Which would be 1 over square root of n, which is 1 over n to the what? 1/2? Okay. You got your bn. Okay. So now let's look at the limit of an over bn. I could go straight to something like this. Okay, and I think we get what? Limit of n over n minus 1. Is that true? And again, we get the limit. If I divide everything by n via calculus 1, divide by n every term. So this is a calculus 1 question. And then this limit is 1 again, which is positive and finite. So what does that mean then? Do you guys know about this series? What kind of series is this? This is a what? This is a divergent p-series. Is that true? Isn't that a divergent p-series? So then that means this series diverges by the limit comparison test. Okay, let's give you guys another one here. So here's my what? an. So this particular series, what does this behave like? If I remove the constant, that 1 over the cube root of what? Into the 4th? So I'm going to remove this constant term, okay? Now, this is going to be, if I simplify this, 1 over the cube root of 3, the cube root of n to the 4th. I can pull out my constant, the cube root of 3. 1 over n to the what? 4/3, I think? Okay. So I can use this as that bn, by the way. So you say this is the limit of an over bn one over cube root 3n to the 4th plus 1 divided by 1 over 4 to the third n to the 4/3. So I'm just going to write it horizontally because I think it makes this easier. 3n plus 4 plus 1 times cube root of n to the 4th here. Okay. Just doing the algebra. Limit now. It's really the cube root of what? N to the 4th? 3n to the 4th plus 1. Is that true? Now note, the limit of n to the 4th over 3 to the n plus 1. I got to take the limit of what's under this radical. Right? And we're going to do the calculus 1 approach. Divide everything by the highest power down there. Limit n goes to infinity. 1 over 3 plus 1 over n to the 4th. And that equals 1/3. I believe so. Is that true? So this limit is the cube root of what? 1/3, which is positive and finite. That's what you're looking for. So what that means is, since this series is a what? What kind of series is this? Is this a convergent p-series or divergent? Is that a convergent p-series? This converges by what? Limit comparison test. Here's our AN. So this series behaves like, remove this constant here, right? Remove that constant. So that's 1 over 2 to the n, which is 1/2 1 over n. Now, you guys know this is a divergent what? Harmonic series diverges. So I can use this as Bn. So that the limit of the ratio of An to Bn is the limit of 1 over 2n plus 3 divided by 1 over n, which will be your limit now, 1 over 2n plus 3 times n, right? The limit of n over 2n plus 3. So use some calculus. Divide every term by n. 1, 2 plus 3 over n, and that's going to be 1/2. And again, that is finite and what? Positive. So this series diverges. This is a very famous divergent harmonic series. And it doesn't matter if you have 1/2 times it, it's still going to be divergent, right? 1/2 times infinity. So that means this series diverges by limit comparison test. No, this is a harmonic series, 1 over n. Well, yeah, when p is 1, I mean, you can kind of look at that, but it still diverges because it has to be bigger than 1 for convergence. So it's divergent. I remember this as a harmonic series, 1 over n. We did this by the integral test, too. We show that this is divergent by... Yeah. This example is very interesting. Okay, so like this is a very interesting kind of question. This is the AN. But then the question is, what does this behave like? Remember, we've been getting rid of a constant, which is thought of as like a non-dominating term here. So you might say, well, what do I get rid of now? You don't have any constants, right? Well, the terms that really dominate are 4 to the n and 6 to the n. Even though you don't have constants to get rid of, we're going to get rid of those n's here. And then this series behaves like 4 over n, 4 to the n power over 6 to the n power. And that's going to be 4 6 to the n, which is a convergent geometric series, by the way. Right? Or is 4 6 or 2/3. But we got to look at the limit of an to bn. So this is now, this is the bn. This one or this one, right? Oops, I got to put divided by. Sorry. Okay, so now here you might say, what happens now? Well, if we distribute, okay, n 6 to the n plus 24 to the n over n 4 to the n plus 24 to the n. Okay, so then the question is going to be now, well, what do we do with this? right? Well, we're going to try to do a calculus 1 approach, I think. Okay. Divide every term by what? That 24 to the n. Let's see what we get. N 6n over 24 to the n plus 24 to the n over 24 to the n over n 4 to the n over 24 to the n plus 24 to the n over 24 to the n. So this limit is now going to be n over 4 to the n plus 1 over n over 6 to the n plus 1. Okay, and so the question's really going to be, note, you want to know what the limit as n goes to infinity of n over 4 to the n, and also n over 6 to the n. I'm going to say that this equals 0. Do you guys know why that's 0? Why is that 0? Yeah, your denominator is exponential increasing and the numerator is not. So those things go to 0, which really means this limit is 1, which is positive and finite. Okay? But this thing goes to 0. Now, if you might say to me, well, how do I really know? Well, go back and use what? Calculus 2, and then infinity over infinity. So by L'Hopital's rule, I have the limit 1 over natural log of 4 to the x, and that equals 0. So the point I want to make is you could deduce simply the ratio of the numerator to the denominator, and that really both of these go to 0. So 0 plus 1 over 0 plus 1 is 1 over 1, which is 1. And so, ladies and gentlemen, you got this nice what? Finite limit. And so this is a convergent geometric series, which means this is a convergent series by the limit comparison test, LCT. Anyway. Let's get this over here. So, ladies and gentlemen, if you go to my website here and you go, oh, yeah, we already know about what's going on in our future. Good. But if I go to this online transition here, I do have some additional examples if you want to see this for limit comparison test, I think. Yeah, right here. You know. Comparison, limit comparison. Let me see. What do I have here? Comparison, limit comparison. I guess there's some additional right here as well. I don't think they're the same. Only 5 likes. Yeah, I don't think they're the same, but Yeah, who knows? I don't know. But ladies and gentlemen, you do have